Welcome everyone to the Fall 2024 course on Combinatorics and Words. My name is Mehdi, and I will be your lecturer for this exciting journey into the fascinating world of the combinatorics and its application to the sequences and words. This course is being hosted by Lomonosov Moscow State University in collaboration with MIT. Throughout the semester, we will be exploring the mathematical structures and problems related to sequences of symbols, one of the key areas in the theoretical computer science and modern mathematics. I look forward to diving into these topics with all of you. Today, we will begin our journey with Lecture 1 titled Introduction and Connection, which lays the foundation for the rest of the course. We will be covering several key topics to ensure everyone is well oriented. First, I'll give a brief introduction to combinatorics on Word, what it is, why it's important, and its applications. Next, we will go through some basic terminologies that you will need throughout the course. Familiarizing yourself with these terms is crucial as they will frequently come up in lectures, assignments, and readings. Afterward, we will touch on some classic theorems in combinatorics, which are essential building blocks in this field. These theorems give us insight into the mathematical properties of words and sequences. Then, we'll explore connections, how these areas of combinatorics ties into the other branches of the mathematics, computer science, and even theoretical linguistics. Finally, I'll point you toward the main sources we will be using throughout the semester, including textbooks and research papers that are core to this subject. By the end of this lecture, you should have a solid understanding of what to expect and how the different topics we'll cover are interconnected. An interesting fact about combinatorics on words, often abbreviated as COW, is that it has its own specific classification in the mathematics subject classification MSc system used by MathScience. This is a great way to appreciate the importance and growth of this area over time. The relevant code for COW is 68R15. To break this down, MSc code 68 refers broadly to computer science, an area that's been classified since 1940, showing the long-standing link between computer science and mathematical frameworks. Within that, 68R is more specific to discrete mathematics in relation to computer science, which was officially established in 1980. Discrete mathematics forms the theoretical foundation for many of the algorithms and structure we will be studying. Finally, the code 68R15 specifically refers to combinatorics on Word, recognized as an independent area of study in 1991. This classification reflects how COW has become a critical part of both computer science and mathematics over time, and it underscores its relevance in the topic like pattern matching, automata theory, and symbolic dynamics. This classification makes it easier for researchers and students alike to access relevant papers, theorems, and discussions related to our course topic. Now, let's dive into some basic definitions that are fundamental to combinatorics and words. First, we define an alphabet, which is simply a finite set of symbols. For example, we might use the binary alphabet 0 and 1, or a set of letters such as capital A, capital B, capital C, capital G, and capital F. Or even symbols representing directions like up, down, left, and right. So the key here is that the alphabet is finite. So be careful. And every word we work with is constructed using symbols from this set. So next, we define a finite word. A finite word, or an alphabet A of length L greater than or equal to 0 is a map like W from the set 0 till L minus 1 to the alphabet A. In simpler terms, this means a finite sequence of symbols with a length determined by L. Now, we extended this idea to infinite words. An infinite word, or A, is a map like W from the natural numbers N to A. Here, the sequence of symbols doesn't stop. It goes on forever. Lastly, we have bi-infinite words, which are sequences that map the set of all integers Z to A. This means word extended infinitely in both directions, both positive and negative, like a two-sided infinite tap of symbols. These definitions lay the groundwork for understanding how sequences and words are manipulated and studied in combinatorics and words, and we will build on these as we move forward. Okay. Okay, let's now introduce some basic notations that we will use frequently throughout this course. First, epsilon denotes the empty word, which is simply an empty sequence with no symbols. This is an important concept in combinatorics and word, as it serves as the neutral element for concatenation operations. Next, A star represents the set of all infinite words over the alphabet A. This includes the empty word epsilon, as any set of words should account for the possibility of having no symbols. Moving on, A plus is the set of non-empty finite words over alphabet A. Formally, this is defined as A plus equal to ASR minus epsilon, meaning it's the same as ASR but without the empty word. Then A to the power n refers to the set of all words of length n over over the alphabet A. For example, if we were looking with the binary alphabet 0 and 1, A to the power 2 would be 0, 0, 0, 1, 1, 0, 1, 1. Similarly, A to the power less than equal n is the set of words of length at most n. This would include words of length 0 through n. So if n, which is equal to 2, this set would include the empty word epsilon, all words of length 1, and all words of length 2. Finally, a to the power natural number, or a to the power omega, which represents the set of infinite words over the alphabet A. These are sequences that continue indefinitely without a fixed length. These notations provide a powerful and concise way to describe different types of the words and will appear regularly in our discussions and problem solving throughout the course. Now let's look at some basic examples of finite words using different alphabets. We start with the binary alphabet, which is one of the most common alphabets in mathematics and computer science. Here our alphabet is 0 and 1. With this we can form finite words such as 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. So these are sequence of zeros and ones of varying lengths, and each sequence is a word over the binary alphabet. Next, let's consider an alphabet composed of letters such as A and B. Using this alphabet, we can create words like A, ABA, BBA, ABBB. So as you can see, just like with binary, we can form words of varying length using only the symbol A and B. So lastly, consider an alphabet of symbols. For example, minus, plus. Using this alphabet, we can create words such as plus, plus, minus, minus, plus, minus, and minus, minus. The rules for forming words are the same as before. It's just the symbols are different. If you look at and using instead of A, 0, or plus, it would be the same. These examples illustrate how the concept of the finite words applies across different kinds of alphabets, whether they consist of numbers, letters, or symbols. This flexibility makes combinatorics on words applicable in various fields, from coding theory to formal language theory. Now let's look at an example of an infinite word using an alphabet and the alphabet 0 and 1. In this case, we can create an infinite sequence like 0, 1, 1, 0, 1, 0, 1, which belongs to a to the power n, the set of all infinite words over the alphabet A. Similarly, the sequence 0, 1, 0, 0, 1, 0, 0, 0, 1 till blah, 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 0, 1, blah, 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 is another infinite word that belongs to a to the power n. But how do we construct such a sequence? Let's define an infinite word W, like A1, A2, go to infinity, where each AI is either 0 or 1. We can create a rule to determine each AI based on the properties of I. In this case, we can define AI as follows. AI is 1 if I is a prime number, and AI is 0 if I is composite. These give us an interesting infinite word that encodes mathematical properties into a sequence of zeros and ones. For example, positions 2, 3, 5, and 7 in the sequence will be 1. Since these are prime numbers, while positions 4, 6, 8, 9 will be 0, since they are composite. This example shows how infinite word can be constructed systematically and how they can represent various types of data, from number properties to more abstract concepts in coding and language theory. Next, we will define formally the length of a word, denoted by like absolute value of W. The length of a word W in A star, the set of all finite words over an alphabet A, is simply the number of the occurrences of letter or symbols in the word. If we have a word like W, define it as a A1, A2 till AN, where each AI belongs to the alphabet A, then the length of the word W is N, as you can see. In the other words, the length is just the number of symbols in the word. For example, if the word would be W, which is equal to 0110, its length is 4, as it contains 4 symbols. On the other hand, the empty word, as you can see, denoted by epsilon, has a length 0, because there are no symbols in it. So absolute value or length of 0 is 0. This definition of length is a fundamental as it allows us to measure and work with words of varying sizes in combinatorics. Okay. Okay, let's now discuss an important result in combinatorics and word known as a fine and Wilf theorem. This theorem provides us with a useful condition related to the periodicity of finite force. The theorem states the following. Let W be a finite force with two periods P and Q. Of course, it should be a positive integer. So the length of the word W is denoted by, we know that this notation in the previous slide. The theorem gives us the condition that if the length of the W satisfies, the length of W greater than equal P plus Q minus GCD of P and Q, where GCD of P and Q is the greatest common divisor of P and Q. Then the word W is also periodic with a period equal to GCD of P and Q. What this result asks is that if a word, actually, what this tells us is that if a word has two periods and its length is sufficiently large, the word will actually have a single period. It is the greatest common divisor of the two given periods. This result helps in the understanding the structure of periodic sequences and plays a role in various applications such as string matching and pattern recognition. In essence, this theorem gives us a way to reduce two periodicities to a single periodicity provided the word is long enough. Hey, in this example, we are given P which is equal to 5 and Q is 8, and the word W is ABAAB, which repeats the sequence. The word W has both periods of 5 and 8, meaning that repeating ABAAB every 5 symbols and every 8 symbols will generate the same word. Let's now apply the find and Wilf condition. First, we calculate the greatest common divisor, GCD of P and Q. The GCD of P and Q here, because they are 5 is a prime, and the GCD of 5 and 8 is a 1 because they are relatively prime. So now let's apply inequality. It should be 5 plus 8 minus 1, it would be equal to 12. This is the length of the W is at least 12, then let me write it in the board, just a second. So as I said, let's apply the inequality. We have W, we don't know what's the length of W here. Okay, greater than equal. Okay, and now P is a 5, Q is 8, and GCD of these two numbers, GCD of 5 and 8 is 1. So it's minus 1. So which is equal to 12. So it means W should be at least 12. At least has 12 letters. So if the length of for W is at least 12, then W must have a period of GCD of 1, and this means the entire word W repeats after one period, and this condition holds even throughout. Initially has two larger period 5 and 8. So this example demonstrates how Phi and Wilf's theorem reduces two periodicities to a single periodicity when the word's length satisfies the given conditions. Okay. Now discuss three important concepts related to words, factors, prefixes, and suffixes. So we start by defining two words, U and V, which both belong to A plus, non-empty finite words. Meaning they are non-empty finite words over the alphabet A. So first we say that U is a factor or substring of V if we can express V as V, which is equal to V1 U, W1 U W2, where W1 and W2 are other words that when concatenated with U for the word V. Essentially, U is a factor of V if it appears as a continuous subsequences somewhere in V. Next, U is a prefix of V if V is equal to UW. This means that U forms the beginning or left part of V. We also have a notation for this. We use this symbol, which indicates that U is a prefix of V. Finally, U is a suffix of V if V is equal to WU. In this case, U forms the end or right part of V. This is essentially the opposite of a prefix, as word U appears of end of V. These three concepts, factors, prefixes, and suffixes, help us break down and analyze words in different ways, whether we are dealing with coding theory, text algorithms, or formal languages. Understanding how words are built up from smaller parts is essential. So now let's look at the concept of a square-free word and the key theorem associated with it. A word is called square-free if it does not contain any consecutive repeated factors. In other words, there are no two adjacent and equal substring within a word. The theorem states that there exists a word over the ternary alphabet that does not contain two consecutive equal factors. Actually, the ternary alphabet consists of the three symbols, typically 0, 1, and 2. This theorem confirms that it's possible to construct a word using this alphabet that is square-free, meaning it contains no repeated adjacent segments. This result is important in both combinatorics and theoretical computer science because it shows that it's possible to avoid certain patterns even when working with a limited set of symbols. So square-free words are useful in areas like coding and pattern matching and the study of infinite sequences. Let's see one example. In this example, we consider a word with using the ternary alphabet A, B, C. The word can be like this. You can see in the screen. So notice how this word does not contain any consecutive repeated factors like A, B, C, A, or A, B, C, A. A, B, C, A, B, C, A. So which would be a square, a repetition of the same factor twice. More generally, it avoids any consecutive repetition of the same substring denoted as XX for any finite substring X. For instance, you won't find the substring ABC or any other pattern of the form XX. This confirms that the word is square-free, which is precisely what the theorem guarantees. This example demonstrates how a square-free word can be constructed, and it serves as a foundation for applications in avoiding repetition patterns in various contexts, such as a formal language and combinatorial algorithms. So now we will talk about connections. Okay, now explore how algebraic structures related to words over an alphabet. The set A star, which is the set of all finite words over an alphabet A, forms what is called a free monoid under the operation of concatenation. In algebra, a monoid is a set equipped with an associated binary operation and identity element. In this case, our operation is word concatenation. Okay, so the identity element in this monoid is the empty word. Epsilon. This is because when we concatenating any word with empty, the word remains unchanged. For example, AB concat with epsilon, which is equal to epsilon concat with AB, which is equal to AB. This shows that the empty word acts as a neutral element in the operation. Concatenation itself follows the rule of when you concatenate two words, you simply join them together. For instance, AB concat BCA is ABBCA. Here, two words AB and BCA are concatenated to form a single word ABBCA. Now let's discuss about this remark. We can also explore other algebraic structures such as semigroups and groups, while monoids have an identity element but may lack inverses. Groups are more structured as every element has an inverse. In the concept of combinatorics on words, we generally focus on monoids, but these structures open up a rich field of exploration. Now let's explore an important result in algebra known as the Novikov-Adian theorem, which was proven in 1968. The theorem states for every odd number n with n greater than 4,381, there exists infinite finitely generated group of exponent n. Let's break this down. A group is said to have exponent n if for every element g in the group, the relation g to the power n, which is equal to e, holds where e is an identity element of the group. We'll see in the next slide more precisely. This theorem asserts that for sufficiently large odd number, n greater than 4,381, there exists a group that are both infinite and finitely generated, meaning they can be generated by a finite set of elements while still satisfying the condition that every element raised to the power n is the identity element. The significance of this result lies the fact that we can construct groups with very specific properties, infinite size, finite duration, and a controlled exponent. These kind of the group are critical in the areas of algebra related to group theory and particularly important in understanding structures in like free groups, combinatorial group theory, and other algebraic systems. This theorem was breakthrough at the time, offering a new perspective on infinite groups and their properties. Let's dive a bit deeper into the Novikov-Adian theorem and its connection, the famous bounded broadside problem. As we discussed earlier, the theorem states, we have it in the screen. Now let's clarify what the exponent of the group means. As I promised to you, we have it in the slide. The exponent of a group G is the smallest number n such that for every element G in G, capital G, raising G to the power n results in the identity element E. Mathematically, we expressed this as G to the power n, which is equal to 1 for all G in the group. This is a key concept in group theory, as it helps us understand the structure and behavior of groups with respect to repeated operations. Connection to the bounded broadside problem. This theorem by Novikov and Aryan is actually a solution to a long-standing mathematical challenge known as a broadside problem. The question posed by this problem was whether for a fixed exponent n, every finitely generated group of exponent n is finite. What Novikov and Adian prove is that for sufficiently large odd exponent, especially n greater than 4381, there do exist infinite groups with a fixed exponent. This disproved the idea that all such groups are finite, solving the problem for those value of n. Moreover, an interesting aspect of their proof is that it involves the use of square-free words over finite alphabet, which ties this result back into the combinatorics on words and sequences that we have been discussing. Now we'll explore a fundamental result in graph theory, especially related to trees and how they can be represented using words. This is known as a proof-coding tree of trees. The theorem states there is a one-to-one correspondence, bijection between the set of trees with n labeled vertices and the set of the word of length n minus 2 over the alphabet 1, 2 till n. Let's break this down, and later in the next slides I will show you what's going on with one special example. A tree is a connected cyclic graph, and in this case we are taking about trees with labeled vertices. If we have n vertices, each one is labeled uniquely by a number from 1 to n. The prover code is a way to represent these trees as sequences of words. For a tree with n vertices, the corresponding proofer code will be a word of length n minus 2 using the labels 1, 2 till n. This is a bijection, meaning that each tree corresponds to exactly one unique and each word corresponding to one unique tree. This is a powerful result because it gives us a way to encode trees as a simple sequences, making certain type of analysis or enumeration easier. The proof code is constructed by iteratively removing the smallest degree 1 vertex from the tree and recording the label of neighbor, continuing until only 2 vertices remain. This process guarantees that the resulting sequence fully describes the tree. Proofer codes are not only important theoretically, but also practical in algorithms and combinatorial applications, particularly in the enumeration of trees. So let's see what's going on. Actually, you see that. Define the j elements of the coding sequence as with deleting from the tree the list vertex ag of degree 1. Okay, and the j element in S is the unique neighbor of aj. Okay, let's go on. So you see that you have many degree 1 like 2, 7, 8, and 5. You see? And now let's try to delete this guy. Okay. And right now you delete it and write one. Now you need to continue. Okay, still you have these vertices with degree 1, 7, 8, and 5. Let's select one of them. Okay, let's select 5 and after that delete. 5 connected to 4. So you delete 5 and instead of 5 you write the word letter 4. Again, we continue. We have 3 vertices with degree 4, 7, 8. Let's choose one of them. 4. 4 connects to 3. We delete 4. After that, we write 3, the letter 3. So 1, 4, 3. Again, right now, we do the same procedure. I didn't write a circle because you know what's going on. Okay, I'm deleting 3 and write 1. Right now, you select 1 and delete 1 with edges connected to 6 and write 6. Right now, you have 2 vertices, 7 and 8 with degree 1. You delete 7 and write 6, and right now you can delete 8 or 6 and go so on. So you see, this will show this tree. So conversely, consider a word like this, of length n minus 2 over an alphabet with the vertices 1 to n, and this word associated with a tree and with any vertices whose coding given by s. That's it. So let's go to the next part. Dynamical systems, most important part for us. Symbolic dynamics in the first part. In this part, of course, we'll explore the connection between dynamical systems and symbolic dynamics, where we describe the trajectory of a point through a code of symbols. The diagram here represents a rotation system, and the sequence of symbols of the word W captures the movement of a point as it follows the rotation you see here. You have here, you move here, and you move here, here, and here. So the trajectory of the point is mapped to a sequence. For example, you see here when we have in the blue part, you write 1, and when you are in the other part, you write 0. So this sequence, also called rotation, can either be periodic or Sturman. So when periodic words repeat after a certain number of steps, meaning that after some point the sequence of symbol will be beginning repeating indefinitely. But Sturman word, on other hand, are aperiodic but still highly structured. They represent a minimal type of non-periodic sequence that arise in symbolic dynamics and are important because they correspond to irrational rotations. In the context of dynamical systems, Sturman boards describe sequences that encode the orbit of the point under irrational rotations, such as the trajectory never exactly repeats, but exhibits a regular, non-random pattern. This approach helps us better understand the behavior of points under rotational dynamics, through providing a bridge between continuous systems and discrete symbolic representations. Very good. In this part of a slide, actually, now, we will delve into discrete dynamics with the concept of the shift operator and shift spaces. The shift operator, denoted by sigma, act on an infinite sequence of symbols, shifting each symbol one position to the left. Mathematically, we expressed these as, this notation. So you see, if you, this means the position 0, position 1, position 2, and so on. So, position 0 of the word A, and so on, so on, so. So, actually, in combinatorics and word, the word started by 0. We consider a natural number is 0. So this means the symbols at the position A0 is removed and every other symbol is shifted one place to the left. The shift operator is a fundamental in the symbolic dynamics because it represents the evolution of a system over time in discrete steps. So next, we will introduce the concept of the shift space, which is a closed set of infinite words that remains invariant under the operator sigma. In other words, if we apply the shift operator to a word in the shift space, the result is still a word within the same space. This gives us a way to study the behavior of sequences as they evolve under repeated shifts. So let's have one remark. An important property in the context in that of uniform recurrence, a sequence or word uniformly recurrent if every subword, finite segment of the sequence, recurs infinitely often through the sequence. Many properties of uniformly recurrent infinite words are determined solely by their subshift, which is the collection of their subgroups. This ties back to how we can analyze complex sequences through their shifts and subgroups. Okay, very good. So now let's explore the fascinating intersection of number theory and infinite force. We start with the observation that the decimal or k-array expansions of rational numbers can be viewed as infinite force. Irrational numbers, such as square root of 2, cannot be expressed as a finite decimal or repeating decimal, meaning their decimal expansion continues indefinitely without a predictable pattern. For example, decimal expansion of a square root of 2 is 1.4142 blah 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 blah, as you can see in the screen. So we can think of this expansion as an infinite word over the alphabet 0, 1, 2 till 9, where each digit in the expansion is a symbol from the alphabet. So we have one nice question here. What are the properties of such expansions? Are there regularity or pattern that can be discerned in these infinite sequences of digits? For instance, you might ask whether certain digits appear infinitely often, or if the sequence exhibits some other structure's properties. Or we have one nice open problems. It's good things about that. One such open problem related to expansion of square root of 2 is the following. Does the digit 7 occur in this infinite expansion an infinite number of times? So this question is a part of the broader inquiry into how the digits of irrational numbers behave in their decimal expansions. Understanding such properties of rational numbers ties into deep problems in number theory, and many questions about these expansions remain unsolved. Interesting. So, continuing with the exploration of the properties of rational numbers, we now look at the significant result by Adamczewski and Bush from 2007, and this result was published in Annals of Math, the best journal in mathematics. This theorem deals with the complexity function or factor complexity of decimal or k-array expansion of irrational algebraic numbers. What is a theorem? The complexity function denotes as a Pn is defined as a number of the different patterns or subword of length n in the k-array expansion of an irrational algebraic number. And the theorem states for every irrational algebraic number, the complexity function satisfies the condition, limit inf of Pn over n when n goes to infinity is equal to infinity. What does it mean? This result tells us that as n, the length of the subword, increases, the number of the distinct pattern of the length found in the expansion grows without bound. So, and it grows faster than n itself. In simpler terms, the decimal expansion of every irrational algebraic number becomes increasingly complex the longer the subword you consider. So this property of infinite complexity shows that the expansions do not settle into predictable repeating patterns. Instead, they exhibit a growing diversity of subworlds, which aligns with our intuition that irrational algebraic numbers are highly complex or random in essence, though they are deterministic. These theorems are profound implications in number theory as it connections the dynamics of number expansions of combinatorics and the complexities of infinite worlds. Very good. Okay, now we want to talk about references. Okay, as we conclude this section of the course, I wanted to point you to one of the key references in the field, algebraic combinatorics and wars by Lotterie, published by Cambridge University Press in 2002. And this book is a comprehensive resource that covers the vast landscape of a combinatorics and wars. And it explores the fundamental concept we have seen discussing, including, for example, algebraic structures and word, combinatorial properties of words, application to coding to and formal languages. And so this book is a part of the Encyclopedia of Mathematics and its applications series, and it's an essential text for anyone looking to gain a deeper understanding of the mathematical theory behind the words and sequences. So I highly recommended this book as a detailed and rigorous references in the rigorous reference for both fundamental concepts and advanced topics in the field. If you are interested in exploring more about combinatorics and word, this is an excellent starting point. Actually, it has mathematical it has mathematical flavor. But the next book we will use in some part, it would be not, another essential reference for this course is Automatic Sequences, Theory, Applications, Generalization by Jean-Paul Alouche and Jeffrey Shalit, published by Cambridge University Press in 2002. This book is fundamental resource on the topic of automatic sequences, which are sequences generated by finite automata. Automatic sequences have applications across several domains, including number theory, theoretical computer science, combinatorics, and more. In this book, the author covers the theory behind the automatic sequences, their applications in various areas such as formal languages, and the generalization of these concepts to broader contexts. So the book provides a comprehensive introduction to both the mathematical and combinatorial aspects of automatic sequences, making it a valuable reference for everyone looking to explore these topics in depth. If you are interested in how sequences can be generated and analyzed using automata theory, this is an excellent book to consult. And actually, it has more for computer science people. So before we finish, I would like to bring everything together throughout the two-day lecture we have. Explore the variety of the concept, the bridge, combinatorics, algebra, dynamical systems, graph theory, and number theory. And we started with the fundamental of combinatorics on boards and discussed key concepts like square-free words and how words intersect in algebraic structures like monoids. These ideas seamlessly contact with deeper question in algebra, as we saw in the Novikov-Adian theorem, the fascinating result of infinite groups with bounded exponents. We then move the graph theory, where the proper coding of trees illustrated the power of bijections in the graph representations. These concepts of coding led us into the realm of dynamical systems, both symbolic and discrete, where we learn how sequence and shapes help us understand complex behaviors in both continuous and discrete dynamics. In number theory, we saw how decimal expansions of rational numbers can be viewed as infinite words. The Adamczewski-Busch theorem further expanded on this by showing us how complexity grows in such expansion, linking back to our core ideas about patterns in words. Finally, I would like to emphasize the importance of exploring further by referring fundamental texts such as Lottery algebraic combinatorics on board and Alusha and Jevshel automatic sequence for Michel-Rico in numeration systems. These references provide deeper insights into the topics we have only begun to touch on today. So, to conclude, I hope this lecture have given you a broad understanding of how word sequences and algebraic structures come together in the different mathematical domains, and I encourage you to delve deeper these topics as they offer many fascinating challenges and applications. See you